Buongiorno. Buongiorno. Okay, so what we were trying to do last time is to compute the density matrix.
Mi scusi, professore, fuori fuoco, non si vede niente.
Ah sì, vedo adesso. Buongiorno. Dovrebbe focalizzarsi da solo, non c'è niente. Adesso sembra che l'abbia trovato, forse. Vediamo se l'altro pennarello funziona un po' meglio. Un po' di più. Forse se spengo la luce è meglio per voi, non so. Si vede meglio se spengo? Magari chiudo un po' questo. Com'è?
No, per tenerne una aperta bisognerebbe trovarne una che si apre dall'altra parte.
Infatti sono tutte in questo senso. Sì, perché effettivamente è un po' sfocata sta cosa. Che forse così è un po' meglio.
Sì, ora è meglio.
Okay, so this is the quantity that we want to compute, and actually we did it for the case of free particle, and we have computed in particular for one particle, and in the context of the canonical ensemble. And I think that we reached this conclusion that for one particle, the partition function, canonical, is equal to v divided by lambda cubed, whereas the rho which is equal to e to the minus beta h for n c1, and this is what equal to what was it? 1 over v, and then we have the Gaussian minus 2 pi lambda squared. And there is a 2, which is important, and x minus x prime squared. Where this is the matrix element between x prime rho x of the density matrix. Okay? And then we have discussed the fact that if we change color again, only for that, that at least we can recover. Okay, so the picture in the coordinate space is the most similar with respect to the classical case in which we have the phase space, and that's why we are projecting the rho. We are computing the matrix element of rho in the basis of coordinates, so x prime and x. Okay. And I think we commented last time on the fact that at least from this picture, now we recover the fact that we have to correct the partition function, the canonical partition function, by some factor here that is not important for the moment, but here I have h to the power of 3 for one particle. Okay. Then if I have n particles, h to the power of 3n. Okay. That was introduced classically just for dimensional reasons, whereas here comes directly from the calculation of the density matrix. Okay. So indeed, if particles were independent, completely independent, one would guess classically that the partition function associated with n particles would be v to the power of n and lambda to the power of 3n. But we know that there is an additional factor, which is the n factorial, which is missing. And actually, what we are going at least to motivate is this 1 over n factorial, where does it come from? Okay. So last time we explained the fact that we have to correct the density matrix. Well, so that we have this h to the power of 3 coming from quantum mechanics, and that was present also in the classical case. And now, today we are going to explain, to motivate the reason for which we have to put this additional 1 over n factorial, which is important for the Boltzmann counting story and so on and so forth. Okay. So what we are going to do now to extend the calculation again of the density matrix, now with 2 particles. And this is a little bit tricky, as you will see. Let's try to do it. So now we take 2 particles. And the Hamiltonian now, so n is equal to 2. The Hamiltonian is the sum of the 2 kinetic energy. And we are going to compute, as the last time, this matrix elements. So let me see, x1, now x2, e to the minus beta h, x1 prime, x2 prime, which is the matrix element that is important to compute the density matrix. Well, is the density matrix element, basically, okay, in the coordinate space, which is the situation more similar to the classical case. Okay. Okay, so now it's a matter of doing the calculation. It's a little bit heavy, but let's try to do it. First thing to do is to introduce the completeness as usual, and we do it. So the sum K1, K2, K1 prime, K2 prime, and I have to introduce the completeness. So here you have x1, x2. Here I put K1, K2. K1, K2. Then we have the exponential of the Hamiltonian, e to the minus beta h, K1 prime, K2 prime, K1 prime, K2 prime, and finally x1 prime, x2 prime. Okay, that's it. Okay, so now this can be computed because this is just now we are in the eigenstates of the Hamiltonian, so therefore this is just e to the minus beta e, and for the moment let me indicate with this, where e is K1 h bar squared divided by 2m plus K2 squared, h bar squared divided by 2n. And then I have a delta, and that's a delta 3 of k1 prime delta into k2 prime. No? Good. Now, by using this delta, we can actually remove two of the sums. So then we are left with sum over k1, k2. Let me see if I collected this in a better way. No. And then I have a function. So x1, x2, k1, k1, k2. And then we have the same, but with x1 prime and x2 prime. Now it is similar to the other case. Now we just need to, and this is the tricky part, to now construct these states here. Last time, this is just the plane wave for one particle, so we don't need to do anything in particular. But this time we have to be careful because this state must be correctly symmetrized. And the form is the following. Here, as you remember, if it is fermion or boson, it's different. I have a plus or minus. And here we have the 2 factorial, right? If you have n particles, then you consider the square root of the n factorial, which is the permutation of n particles. Okay, so this is the correct normalization of the wave function in the case in which we have the symmetrization of the states. And here I have u1 k1 of x1 and u k2 of x2 plus minus u k1 x2 times u k2 x1, where the plus is for bosons and the minus is for fermions. Okay, so this wave function is it is symmetric with respect to exchange of x1, x2 with a plus, no, and then it is antisymmetric, and so fermions in the opposite case. Good. So now what we have to do now? Okay, so remember that this 1 over square root of 2. I will just indicate with 2, but remember that this is the 2 factorial or the n factorial that is important at the end to justify everything. Okay, so if I have n fermions, here we have this later determinant, and we will have 1 over square root of n factorial. Okay. Okay, so now we have to proceed with the calculation and see what happens. So now I have introduced, I have to introduce this monster in here and here. Okay. And also, it's good to remember that the single particle wave function uk of x is equal to 1 over square root of the volume times the exponential of k scalar x, as last time. Okay. Good. So now we have to do it, and our matrix element is equal to 1 over 2. This 1 over 2, let me indicate here as 2 factorial, comes from the fact that here you have a 1 over square root of 2 and 1 over square root of 2. Okay. because I have this wave function and this wave function. So this let me keep for a moment this factorial just to remember that where it comes from. Okay. Then there is a volume squared, because I have this guy which is repeated 1, 2, 3, and 4 times. So I have a volume squared here. Okay, volume squared. Then I have the sum of on K1, K2, and let me put here a prime, and I will indicate, I will tell you in a moment what does it mean, this prime. Okay, so then I have the e to the minus beta times h bar squared K1 divided by 2m plus h bar squared K2 squared divided by 2m. And now I have the plane waves, which are the following: e K1 scalar x1 and exponential of I K2 scalar x2. Then I have a plus minus. I have to introduce this term here, K1 x2 and e to I K2 scalar x1. Let me check if this is correct. Yes. Now, this is this. Then I have to multiply by this and consider that this is a complex conjugate. So I have a similar structure, but the k are, well, the x are x1 and x2, and I have to consider the fact that there is a minus. So I should have this structure here, e to the minus I K1 scalar x1 prime, e to the minus I K2 scalar x2 prime, and then I have again plus minus, and here I have e to the minus I K1 scalar x2 prime, K1 x2 prime, yeah, e to the minus I K2 scalar x1 prime, and let's close it. X1 prime, okay. So now let me call this term 1. This is 2. This is 3. And this is 4. Okay. Okay, so now what is the meaning of this prime? Here you have the sum over K1 and K2 that are free, but actually I need to remove the terms in which K1 is going to K2 and K2 is going to K1. Okay, so this removes the terms in which K1 is equal to K2 and K2 is equal to K1, because we have already considered this possibility when symmetrizing the wave function. Okay, the wave function is already symmetrized. This is just a symbol that we will remove in a moment, but that's the reason. Okay, since we are symmetrizing already with respect to K1 and K2, we have to remove in principle in this sum the terms in which K1 is equal to K2 and K2 is equal to K1. Okay, now it's time to do the calculation, and let's do the following. Come faccio? Cancello qua, provo a scrivere because I want to keep this structure here. So maybe I want to remove maybe this, if you have written, and then let me write down, because I want to keep this structure. Okay, so now you have 1 over 2 factorial v squared. Of course, now this v squared comes from the fact that we are considering 2 particles, and actually at the end, I will see that it will be removed. Then we have to do all the sum, and let's try to do it. Sum over k1 exponential over k1 squared divided by 2m, which is this part. And here you have e to I k1 scalar x1 minus x1 prime. Let me check if this is correct, times the sum over k2 exponential of a squared k2 squared divided by 2n. And I have e to the minus, sorry, e to k2 scalar x2 minus x2 prime. And this one thing, which is the product of 1 times 3. 1. I'm multiplying this term by this term. Okay, so then I have plus minus that comes from here. Plus minus. Now you have to do, let me see what I did, 1 times 3, and then I have 2 times 3. 2 times 3. So, lo scrivo qua, lo scrivo sotto, lo scrivo forse sotto così è più chiaro. Okay. So then I have the sum k1 e to the minus h squared k1 squared divided by 2m. And here you have e to the I k1 x2 minus x2 prime. Prime. Aspettate che forse ho sbagliato questo. Dove stiamo? K1 x2 minus x1 prime. Sorry, x1 prime. Okay, this one. Then the sum over k2 e to the minus h squared k2 squared divided by 2n, and then I have the exponential. Here I should have a k2, and here I have a x1 minus x2 prime. X1. This is the product of 2 times 3. 2 times 3. And also I need to recover a beta that was present here. Beta, beta, and beta. Of course, so I have done this times this, and this times this. And then this a plus minus. Okay, now for reasons that are due to the fact that the sum was a sum prime, I have excluded, I'm not considering the product of, not considered, the cross of 1 and 4, and the cross of 2 times 4, So I'm not multiplying this times this and this times this, because the sum prime was excluding the cases in which K1 is equal to K2, so it's substituted to K2 and K2 is equal to K1, okay? And I'm not considering those cases because they are excluded, and indeed one can check that one can obtain the product 1 times 4. I've done it yesterday night again, times 4, by changing K1 with K2 and K2 K1 into 3. 2 cross 3. 2 cross 3. Okay, let me see if this is true. I should be correct because I have tried to do it yesterday again. So in 2 cross 3, which is this term here, is that if I substitute K1 with K2, I should have a K2 x2 minus x1 prime, and that should correspond to the product of 1 and 4. K2 x2 minus x1 prime. It should be correct. And, well, also for the other case, this will be K1 x1 minus x2 prime and x1 minus x2 prime. So it should be correct. And I checked it yesterday again. Okay. So since the sum was done in a way to exclude the cases in which K1 is going to K2 and K2 is going to K1, I have to consider this fact. And so I'm excluding indeed the products in which I can have those exchanges. Okay. It's a little bit tricky, but if you think about it, it's correct. And then, of course, now those sums are normal. Okay, there's no prime here. I'm summing over all K1, K2, K1, and K2 in those cases. Good. Now, it's almost done in the sense that now we have this separated sum, and we know how to deal with them because we computed them last time. We have to substitute the sum with an integral, and we also know the result of that integral. So now the sum over k will become v divided by 2 pi cubed integral over dk, okay, as we did last time. And also remember that we have computed already those integral were done last time because we have to it is almost a Gaussian integral, but for the fact that we have to introduce an additional term in order to complete the square. And actually the formula that will be used is this one, x e to the minus beta h x prime is for one particle that we derived last time is equal to 1 over lambda cubed, and here you have the exponential of minus 2 pi divided by 2 lambda squared x1 minus x, or this x minus x prime squared. Allora questo qua, no? Okay. So basically, to all of the sum, and this I have to substitute the structure here. Okay. And there is a volume that should cancel exactly with the volume that we have in front of this. Okay, because I have a volume from here and a volume from here, the volume squared that cancels with this. And so at the end, so you put the structure let's call it asterisk, in this equation, let me call it Pallino. Okay, so, and to make the calculation simple, let us consider the diagonal terms, otherwise it's a mess. X1 coincident with X1 prime, and X2 with X2 prime, which is, if you want, the diagonal terms of the matrix of the density matrix. Okay. So now the result should be the following. I have this 1 over 2 factorial, which was the basic reason for doing this calculation. Well, not only this one, of course. And then I have a lambda, which is a lambda squared, lambda cubed squared, which is 1 over lambda 6, the power of 6. Because I have a lambda cubed coming from here, lambda cubed from here. And this is a factor which is in common among this and this. Then I have a plus and plus minus. And here I have the exponential. Where does the plus come from? The 1 come from? Well, the fact is that I'm putting x1 equal to x1 prime and x2 equal to x2 prime. So those are just Gaussian integrals. Whereas here I have the linear term in k. Okay, and this was and this corresponds to this. Okay, whereas if x is equal to x prime, I just have 1 over lambda cubed. Okay, so those terms will just have 1 over lambda to the power of 6. And also those terms contribute with 1 over lambda to the power of 6, but they have the exponential structure here, which is the following. So here I have minus 2 pi divided by lambda squared. And here you have x2 minus x1 minus x2 square modulus squared. And I think it should be correct. So here there is a 2 missing because this is squared. Okay, I have this times this time. Okay, k1 and k2 I'm integrating over them, and here I have x2 minus x prime, which is actually x2 minus x1 and x1 minus x2, and we know how to deal with those integrals, and the result was this one. Okay, but I have to do a square. Bene. So now let me collect the result. So what we were computing, it was the matrix element, but actually I'm considering just the diagonal terms, x1, x2, and of e to the minus beta h, x1, x2, and the result is the following, is 1 over 2 factorial, lambda to the power of 3 and to the power of 2, where I'm stressing the fact that we have 2 particles. And then I have a 1 plus minus e to the minus 2 pi. And here you have a lambda squared. And here you have x1 minus x2 square modulus. and that's it. Okay. Now we can compute also the canonical partition function of two particles now, which is just the trace of this guy here. And what is the trace in this case? Since we are computing this matrix element in the coordinate space, is just an integral, no? It's twice the integral. So it's dx1 dx2 of x1 x2 e to the minus beta h x1 and x2. Good. Now we can just substitute this, and here you have dx1 dx2, and I can copy the structure that I have there. So I have a 1 plus minus e to the minus 2 pi lambda squared x1 minus x2 square modulus. And I have a factor, overall factor of 1 over 2 factorial lambda 3 to the power of 2. Okay. Okay. Now this is equal to 1 over 2 factorial lambda 3 to the power of 2. Then we can deal with the first integral, which is just the x1, the x2 of 1, which is volume squared. So we have volume squared. Then I have a plus minus coming from here. Here we have dx1, dx2, exponential of minus 2 pi lambda squared x1 prime x2 x1 minus x2 square modulus. Let's close it. Quindi questo qui va bene. Okay, now I have to deal with this integral, and actually there is a trick that we can use. This is a double integral in x1 and x2, but actually here the dependence in the function is just from the difference. So then I can introduce two variables. Let me call x, let's say x1 minus x2, and let me call r, well, let me maybe do this. X will be the x1 plus x2 divided by 2, which is the coordinates of the center of mass, if you want. And r, just the difference instead, x1 minus x2. So you compute the Jacobian is equal to 1. Okay, and this double integral becomes an integral over dx, which comes, which will contribute with 1 over with a factor of b. Okay, so let me write down first. So you have a b squared plus minus. I will have a volume here, volume times the integral over dr of what is left there. So e to the minus 2 pi lambda squared, and now I have r squared. E dovrebbe essere tutto. Ok. This was the canonical partition function of two particles. Lo so, 12 va bene. Ok, Okay, so now let me collect, okay, one has to do this integral here. Let me sketch how to do it. Of course, this is a 4 pi integral over dr, r squared and e to the minus 2 pi divided by lambda squared, and this is the r squared where I indicated with r the modulus of r. Okay, it's not interesting to do this integral, you can do it by parts, no? Vado per parti questo. And I will just write the result. Of course, what is important is that I have this lambda there, which contains temperature inside. And if you do the calculation, basically you get the following result. 1 divided by 2 factorial, lambda cubed to the power of 2, and b to the power of 2, which can be collected. Then I have 1 plus minus. Let me write the result first. 2 lambda cubed divided by the volume. This 1 over volume comes from this because I'm collecting b squared, and then I have to correct this 1 over volume. Okay, and the lambda to the power of 3 comes from the integral, and here I have 1 divided by 2 to the power of 5. This is the final result. Where this factor of 2 also refer the fact that we have two particles. Two particles. That's why I have not simplified with these 2 to the power of 5 that we will recover later as a factor, as an additional factor. Okay, so this is the result. Now you see that in this calculation, now you have the canonical partition function of free gas of two particles in contact with the thermal reservoir. And you see that the prefactor is correct. So a prefactor is 1 over 2 factorial and lambda 3 to the power of 2 and b to the power of 2. That is corresponds to the classical case. Okay, is just the classical. Partition function associated with two particles, that was d to the power of n, blah, blah, blah. Okay, so the prefactor is correct, and it is the classical case. And you see that in here there is a correction. Okay, let me write it here. The correction with respect to the classical. With respect to the classical. Is this guy here? So it's proportional to 2 divided by the volume times a lambda cubed, apart from this 1 over 2 to the power of 5/2, which is not important. Now, what I can think about here, so what I can basically say about this guy is just the product of the density, because it's 2 particles divided by the volume, times lambda cubed. So if you want, this is just n times lambda cubed. So again, we recover that if n times lambda cubed is much smaller than 1, which means small densities, okay, or large temperature, all the two things together, then the correction, the quantum correction, is approaching 0. No? So the classical case is obtained when the density times lambda cubed is a small number, which means small temperature, small density, large temperature, or if you want, the interatomic or interparticle distance is much larger than the de Broglie wavelength. Okay, so we recover a nice result. So basically, this structure is interesting because I have the classical result, which is this prefactor. Then I have a correction coming from quantum mechanics, even though we are in a free particle case, but there is a correction due to quantum mechanics that scales exactly as n to the n times n times lambda cubed. Okay, and somehow at the beginning of this lecture, we said that this is the important quantity that one has to consider in order to see if we are in the classical regime or in the quantum regime. Okay. Okay, I think that about this, there's not much to do. And of course, we are happy that we have found the 1/2 factorial. Now, if I would compute, let me comment on this first, the case with n particles, which is a very difficult task, because then here I have the exchange of just one particle among two particles. In the case of n particles, I have n factorial terms. So it's a very complicated situation, no? So I have all the possible exchanges of particles 1 and particle 2, 3, and 4, etc. You clearly see that it's a very complicated structure. And indeed, for n particles, the canonical partition function, in any case, would have just the usual prefactor, which is this one, v to the power of n, which is the classical. Then I have a 1, and then here I have the quantum correction. Okay, which comes from the exchange of two particles, exchange of three particles, 4, 5, etc. Okay, but the computing those corrections in the canonical ensemble and in this basis, because we are working with coordinates, it's a very difficult task, and actually it's not very useful to do it, because now we understood where does the classical case come from. But we will compute, we see, maybe not today, but next time, the grand canonical partition function in any case. So you probably will come back later. Now let me comment on this also. This is the canonical partition function for two particles, and let me also write again the matrix element of rho, which is proportional, but for some normalization, this is proportional to 1 plus minus e minus 2 pi lambda squared x1 minus x2 square modulus. Okay, now so let me comment on this structure a little bit. This structure here tells me that if x1 is equal to x2, so I have two particles in the same position, this is 1, and so this is 0. So the matrix element in this case is 0. Okay. Whereas if x1 is equal to x2, also sorry, the case of fermions and the case of bosons, of course, I have to distinguish. So for bosons, I would have if x1 equal to x2, here I have a factor of 2. No? So this equal, so this matrix element is proportional to 2 times this normalization, whereas for fermions, this matrix element here is 0. Because in this case, x1, x2, and this 1 minus 1 is 0. Okay. So that corresponds, so that encodes, if you want, the fact that where for bosons, they like to be in the same states. And this is something that you know already. And also in coordinate space, they like to be in the same position. So there is an enhanced probability to find them in the same position. Whereas for fermions, it's just the opposite. Okay, fermions cannot be in the same position. And if you want, there is a sort of interaction that can be seen already at this level. Here, the fact that I have two particles and the exchange and the symmetrization of the wave function is encoded in this correction. So somehow it's like that. I mean, somehow the fact that I have this wave function symmetrization is similar to including an effective interaction for which the particles are not independent anymore. Okay. So this quantum correction, due to the symmetrization of wave function, can be thought as a sort of effective interaction. And indeed, since rho has the structure of e to the minus beta h, one can introduce a sort of potential like this, e to the minus beta v, where v is an effective potential provided by this formula. V, the sort of effective potential. So if you want this one, it was the kinetic part, and this is the contribution due to the effective potential that can be written as 1 minus over, well, the log of this quantity. So 1 minus 1 divided by beta logarithm of 1 plus minus e to the minus 2 pi lambda squared and x1 minus x2 squared modulus. Okay, so I'm interpreting this part as a sort of potential, as due to a sort of potential, effective potential, and therefore, since rho has a structure of e to the Hamiltonian times beta, this term here will be something e to beta times a potential v. Okay, the prefactor was associated instead with the kinetic term, and I have this effective potential, which is minus 1 divided by beta log of this function here. I can also make a plot of this effective potential. Opla. So if I plot V as a function of x1 minus x2 modulus, I will have something like this for fermions. Which is a repulsion. And encodes the fact that fermions are not do not like to be together somehow. And this comes from minus here, this minus here. Try to make the plot. we get this result. And whereas for bosons, we have the plus there. And I will start with a negative value here, which is 1 minus 1 divided by beta log of 2, and actually is approaching 0 from below. This is an attractive channel. Attraction. Okay. So the fact that we have symmetrized the wave function for bosons and for fermions will provide a sort of effective potential of interaction between particles that clearly has not a classical analysis. And indeed, this is regulated again by the lambda, okay, so that by the Broglie wavelength. So if the temperature is large, then this quantity is basically 0, and I should recover the classical result. Qualche altro commento su questo? Well, okay, let me just comment on this, although I'm not going to do the calculation. When considering the symmetrization of the wave function, I have introduced this 1 over n factorial. Actually, for bosons, the calculation is a little bit more complicated. Well, not a little bit, but a bit more complicated, because in the case of bosons, I can also have situation in which K1 and K2 are coincident. And the same is true for many particles. So the normalization of the wave function is rather a little bit more complicated, but the final result is always the same, in the sense that the correction is always 1 divided by m factorial, okay? But keep in mind that the calculations that we have done does not consider the proper normalization of the boson wave function, which is a little bit more complicated than the one that we have done here, okay? But I just wanted to say this. Ok, posto questo lo chiudiamo. Okay, so now it's 12, 5 past 12, so let's make a break. And then we continue. Non lo può riporre di nuovo questo. Qui si è defocalizzato di nuovo, non so perché lì decide arbitrariamente. Ecco, forse adesso diciamo. Okay, so what we did before is to compute the matrix element of the density matrix in the coordinate space. Okay, this procedure is complicated, but it's useful in order to recover the classical results. Now what we are going to do instead is to work in a more, let's say, useful basis, which comes basically from the fact that we have derived an equation for the density matrix that was the following. This is equal to minus commutator of rho H. And for thermodynamics, so in equilibrium condition, we have a stationary situation of rho dot is equal to 0. That implies that the commutator between rho and H is equal to 0. And so we can find a basis, a common basis of eigenstates of H and rho, and indeed rho is equal to the minus beta H, okay? So we will work now, we will work with a set of orthonormal and complete states, okay? And what is the entropy? We said last time that the entropy is associated with the density matrix by this equation, so minus Kp sum over n, where now n runs over the set of the complete states, the complete set of states of the Hilbert space, and this is equal to rho n log of rho n, where those rho n are the diagonal terms of the density metric in these spaces. Okay, and okay, so this is the entropy. What is the Helmholtz free energy? Is U minus Ts. And what is U? U is the trace of, this is an observable, and it is the trace of rho times the energy, or times the Hamiltonian. So U is the trace of rho H minus T, what is S is Kb times the sum over n rho n log of rho n. And what is the trace of rho H? Is just the sum over n of rho n En, okay, in this basis. So minus Kb sum over n of rho n log. Good. So now this is the Helmholtz free energy. And we know what I'm going to recover in a moment is the is the part that the rho is e to the minus beta h divided by the partition function. I will derive the result that was actually postulated last time, now from here. So now we minimize, because in thermodynamics, when dealing with fixed temperature and fixed volume, which is the situation of the canonical ensemble, we minimize A, because we are in the canonical ensemble, in which T and volume are fixed. And we know that the second principle of thermodynamics tells me that I have to minimize the Helmholtz free energy. The minimization of this must be done under the constraint that the trace of rho, being a matrix, density matrix, is equal to 1. Okay? So what we do is to use the Lagrange multiplier technique, and we minimize this quantity. So rho n En plus TKB sum over n rho n log of rho n plus lambda. Then I have the trace of rho, which is the sum of rho n. Okay, where lambda is a Lagrange multiplier. Okay, the calculation is very easy, and we have done this in other context. So I will not repeat the calculations, basically the usual ones. So derive with respect to rho n go to 0, and you will discover that rho n is equal indeed to e to the minus beta En, and correctly normalized, this should be divided by the sum over n of e to the beta En. Okay. You can try to do it as an exercise. The calculations are very similar to the ones that we have done at the beginning. Okay, so indeed, the form of rho n that I was assuming before, it is somehow that was postulated, actually can be justified by minimizing the Helmholtz free energy with respect to rho n. Okay, so now let me make just a little comment on the rho n in the limit of large temperature and in the limit of small temperature. So for T going to infinity, I have this 1 over T, and basically all the matrix element of the diagonal terms of the density matrix will be 1 divided by the normalization. So the density matrix will have a form like 1 divided by 0C, and here I have 1, 1, 1, etc. Okay, which means that all the possible energy states are occupied with the same probability. If you want, this is also the situation of maximal entropy. So all En equally probable. I remind you that En is not the energy of one particle, is the energy of one system in the canonical ensemble. Okay, that must not be confused. This is the total energy of my system, and the system is a point of the canonical ensemble. Okay. Now, what happens is that if T is approaching 0, when T is equal to 0 or is approaching 0, I expect that all the members of the canonical ensemble will sit in the ground state. So when T 0, all its systems of the canonical ensemble will have the ground state energy which we call it 0. That of course must be always present because the Hamiltonian in quantum mechanics are always, at least for the normal cases, bounded from below. So there is always a ground state, otherwise the system will be unstable. So there is a ground state that we call E0, and in this situation the density matrix will be something like this. Here, okay. And you see that in this case, all the systems of the canonical ensemble are the ground state, and the entropy is equal to 0, because the entropy, the associated entropy here, is equal to 0. Okay? So this is a sort of justification of what is called the third principle of thermodynamics. That tells us that when T is approaching 0, also the entropy goes to 0. Okay. And it's something that cannot be derived classically, but it has a sort of justification of quantum mechanics based on this kind of arguments. Okay. Okay, so let's continue to work on this basis, which is the most useful one, unless one wants to recover the classical calculation. And let's deal with now a gas of quantum particles, which are free in the sense that they are not interacting with each other, which will bring us to the usual statistical distribution that you know, Fermi, Dirac, and Bose-Einstein. Okay. So now we are dealing with the gas of quantum particles, non-interacting. Gas of non-interacting quantum particles. Okay. Now, the canonical partition function working in the basis of the eigenstates of the Hamiltonian is equal to the sum over n of e to the minus beta en. Okay, we're not working in coordinate space anymore, but we are using the orthonormal set, which is the set of eigenstates of the Hamiltonian. In principle, there could be some degeneracy. Okay, so not all of these. So for this En, there could be some degeneracy that we need to consider in a moment. Okay. And okay, so what are the possible states occupied by a single particle? Okay, so let me make very clear that En is a total energy of the whole system, okay? Whereas each particle will occupy a state
a state which is an eigenstate of the Hamiltonian, which for free particles is also an eigenstate of momentum, and therefore we'll have the standard K or P, which is H bar K. So those are single particle states. Which are the eigenstates of the Hamiltonian or the momentum. Okay? And K is a vector following the standard precision or quantization in a box. This will be something like this: 2 pi divided by r gy, 2 pi divided by r. Okay, where jx, jy, jz are belonging to into the integer number set. Okay. Now let's call with nk the number of particles that are in the state k, okay? Or the occupation number, if you want. Occupation number of state. The number of particles with the sitting, so having k as a wave number. Okay? Now let's write it down now the canonical partition function for this specific situation. This will be a sum over n, but actually this sum must be now done in a slightly different way, because n runs over all the possible states of the orthonormal set, complete set. Now we are running over the nk actually. So let me write first the exponential. So here you have e to the minus beta. And here the energy of the total system will be the sum of the energy of the single particle times the number of particles in that state. Okay, so let me write it down. So this will be the sum over k, so all the states of nk times epsilon k, where epsilon k, let me write it down here, is the standard energy, kinetic energy that we have seen also before for a single particle. Okay. So the role of En here is played, that was the energy of the total system, is played by this guy here, which is the sum over k of nk ek, where nk is the number of particles in state k. Okay. Now here, what is the sum running on? Here, the sum is running over nk, and I consider the symbol to be a set of possible occupation number. So actually here I'm running over several nk, so nk1, nk2, etc. nk3. Because I can have, once I fix k1, k2, k3, and k infinity, I can have several different occupation numbers for each of these states. Okay, so here the sum is not running over n, which is quite general and not very informative at this level, but it is running over all the possible arrangements of my particles in the states k1, k2, k3, etc. Now here, let me put a prime, which is a standard procedure, and this prime indicates that when choosing the states, when choosing the occupation number set, I have to be sure, since I am in the canonical ensemble, that the number of particles is conserved. So the sum of this prime indicates that the set of occupation number must conserve the number of particles in the canonical ensemble. Okay, namely, I have to impose that the sum over nk is equal to n, where n is the total number of particles, and this is the sum over k of the nk. Okay. So this is a complicated situation because now we have infinite number of possible states, okay, and I have to arrange n particles in all the possible ways in those infinite states. Okay, so these are very complicated calculations actually. Indeed, let's try to compute it for the case of two states and for the case of fermions. So let's try to compute this canonical partition function in this basis for two states and two fermions. So case of two fermions and two states, let's call them K1 and K2. Okay. Now, what I have to do here, well, considering the fact that they are fermions, nk1 could be 0 or 1 at maximum, and nk2 will be 0 or 1 at maximum. Okay. So when doing this sum, I have to make the sum prime over nk1, nk2 of e to the minus beta. Here I have nk1 epsilon k1 plus nk2 epsilon k2. Okay, so I'm writing this guy here. I have the sum prime, and then I have a minus beta, blah, 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 and nk1 and k2. Okay, so let me remove the prime. If I remove the prime, here I will have the following situation. I have to sum over nk1 and nk2, taking into account the possibility, the fact that nk1 and nk2 can be 0 or 1. Now we'll have those terms, so e to the minus beta times 0, if you want, epsilon k1 plus 0 epsilon k2 plus similar e to the minus beta epsilon k1 plus 0 epsilon k2 plus e to the minus beta 0 epsilon k1 plus epsilon k2 plus the exponential of minus beta epsilon 1 epsilon k1 sorry epsilon k2 epsilon k. Okay. Now those four terms are not good for us, not all of them, because they are not respecting the conservation of the number of particles. So actually, if I consider the conservation of the number of particles, the only term that survives is the last one. Okay. So only this one, actually, only this one preserves the number of particles. So if you want the canonical partition function, that was the sum prime. Now let me put the prime of nk1 and nk2 of x minus beta h is equal to this. Okay. Now, the situation with two particles and two states is easy to deal with, but you can imagine what a complicated situation I have in the cases in which I have infinite possible values of k, because this is not bounded from above, and particles when n is 10 to the 23. Okay, so very complicated combinatorial calculations that we are not even trying to solve, but actually what we do, and here is the grand canonical ensemble magic, use the grand canonical ensemble in order to remove the constraint of the conservation of the number of particles. So the idea is to use the grand canonical ensemble, so grand canonical partition function, to remove the constraint on the conservation of the number of particles. No, cambiare soggetto. Così. And so what we do now is to write the grand canonical partition function. And actually, when dealing with the quantum gas, it's much better to use the grand canonical for the reason that I explained here. So let's write down the grand canonical partition function. Now this will be a sum over nk as before, where nk means a set of possible occupation number, but without any constraint now. I'm not putting a prime here. There's no constraint on the conservation of the number of particles. Here you have the fugacity to the power of n, so which is z times to the power of the sum over k over nk. Okay, where z is the fugacity. So z to the power of n. And then, okay, as before, we have the exponential e to the minus beta, sum over k of nk epsilon k. Okay. So here I have no limit. Okay, so let me write it in a slightly different way. You have the sum over nk, and by using the definition of the fugacity, I have e to the beta facciamo così, into beta, and then this beta has to multiply the sum over k of mu minus epsilon k times nk. La somma su nk, okay, where I'm collecting nk and nk here, yeah, and here you have a beta mu, okay, beta mu nk and beta epsilon k nk. Okay, this should be correct. Okay, this becomes sum over nk of the set of nk. Now we have the exponential of a sum that becomes a product of exponential. So you have a product over k of e beta mu minus epsilon k times nk. And this is the grand canonical partition function. So that is equal to the grand canonical partition function. Now the thing is that there is a magic here that comes from the fact that we are not conserving the number of particles. So I have no constraints on nk. Nk can do whatever it wants, can go also to infinity. And in such a situation, I can invert the sum and the product. And this actually will lead to a very simple result. You can invert sum and product. To justify this, let me make an example again as before. As an example, take two fermions with stati. Yeah, two states, so K1 and K2, and two fermions with nk1 equal to 0 or 1 and nk2 equal to 0 or 1. And let me consider this case, this situation. So now, in this case, I have to make the sum for this situation. Forse lo scrivo sopra. I have a sum over nk1, nk2, and then I have the product over k, but k has two possible values, and therefore I have two exponentials, which are the following: e to the beta mu minus epsilon k1 times nk1, and the exponential e to beta mu minus epsilon k2 times nk2. Okay, now the sums are decoupled, therefore they are, one can run over nk1 and nk2 separately, and we get these terms here. So 1 plus e to beta mu minus epsilon k1, and 1 plus times 1 plus e to beta mu minus epsilon k2. Okay, where I'm running over nk1, like nk1 can be 0 or 1. If it is 0, then I get 1. If it's 1, it's beta mu minus epsilon k1. Similarly for this term here. Okay. Now let's try to do it by instead summing first and then making the products. So by inverting even this. So now invert sum and product. And therefore we'll have now this time a product over K of the sum over nk of, okay, we use a structure which is mu minus epsilon k minus nk. Okay, as before, now it becomes the product over K, product over K, of when doing the sum, again, consider the fact that a K can have two possible numbers. So K is fixed now because K is in the product, and I have to run over the values of nk, okay, at fixed K. And which are the possible values of K, and K is 0 and 1. And therefore I get again 1 plus e to beta mu minus epsilon K. Now K runs from K1 to K2, and therefore I have, as before, the product of 1 plus e to beta mu minus epsilon Q1 and 1 plus e to beta mu minus epsilon K2, as before. Okay, so that means that we can invert indeed the product in the sum, and this is due to the fact that we do not have constraints on the number of particles in the grand canonical ensemble, and this will lead to the following result that will close the lecture. That is the starting point then for the quantum statistics. So the grand canonical partition function was written as product over K, and here we have the sum over nk and e to beta mu minus epsilon k times nk. Okay, so here I just okay, here I have inverted the now. So before inversion, it was the sum over nk, and those are possible sets, and the product over k of E, well, is in quantity, E mu minus epsilon k. So this was the starting point, and we said that we can invert the sum and the product, and we have this quantity here. Okay, so now let's work out a little bit this. This is the product of K of the sum nk of e to beta mu minus epsilon k to the power of nk. Okay. Now here there is a bifurcation. One was Einstein. In the Bose-Einstein case, these are geometrical series, and therefore the grand canonical partition function will become the product over K of this quantity, which is just 1 divided by 1 minus the exponential of beta mu minus epsilon K. So the grand canonical partition function for a Bose-Einstein gas is the following. No? This nk runs from 0 to plus infinity in the following geometrical theory. Whereas for Fermi-Dirac, the grand canonical partition function will be just product of k. Now the sum will run from 0 to 1, and therefore here just a 1 plus the exponential of beta mu minus epsilon k. Okay. So where I have used the fact that pk can be 0 or 1, whereas in this case nk can be 0, 1, blah, 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 plus infinity. I have no limits. Okay? So once we have the grand canonical partition functions, we can derive all the thermodynamics, no? And this is what we will do next time. The thermodynamics of Bose-Einstein gas and Fermi-Dirac gas. Okay? We will recover some of the results that you know, that you already know, of course, and we will try to make, so to consider some applications as the, for instance, the Sommerfeld expansion and the Bose-Einstein condense, and we will see how much time we have. Okay. Saluti, ci vediamo giovedì.
Arrivederci.
Arrivederci.